Good morning, and welcome to today's Electronic Design webcast. Our topic today is RF Basics for Low-Power Wide Area Networks, sponsored by Texas Instruments. I'm James Mora with Endeavor's Design and Engineering Group. To start, let me explain how you can participate in today's presentation. First off, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. This webinar technology allows you to resize the presentation by clicking the maximize icon or by dragging the lower right corner to enlarge the window. We also welcome your questions during today's event. We will answer as many as possible during the Q&A session following the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on Electronic Design's website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Thomas Emholt is a senior systems engineer at Texas Instruments with 20 years of international experience. His last 10 years have been in the semiconductor industry. You can learn more about our speaker by clicking on the blue speaker bio widget on your console toolbar. Now let me turn things over to our presenter. Thomas, the floor is yours.
Good morning, and thank you for joining this morning. During this little webinar, we are going to have 3 small poll questions, and then also, of course, my main presentation. So the main topic of today is RF basics, and this means talking about what are some of the key features and key items that need to be considered in order to achieve a wireless network. In specific, for this webinar here, considering low power, wide area networks, which are long range. So first, let's do a quick poll question. So what are some of the main barriers for adopting wireless technologies in your industry or your company? The poll are in 4 little questions, and you can hit the submit button. First one is that you have no RF experience inside your company, or maybe it's a lack of time or resources, or that RF technology is seen as too expensive or prohibitively expensive for the type of technologies that you are trying to do, or something other. And then you can hit the submit button right here, and then we should be able to see live here what these polls were. So I'm going to forward this. You see here, we're actually getting a result back here very, very quickly that, and this is not a surprise to me, that the lack of RX experience and also time and resources are some of the main barriers for entry into wireless technologies. And this is why I'm happy that you guys are all here today, and I will go forward to the main presentation. So first, let's have an overview of what LPWAN technologies are. So LPWAN, or any kind of wireless network, can be added to any kind of device or gadget that is being built. And a research paper here by Morgan Stanley showed that over 90% of all applications worldwide in any industry, they're thinking about adding wireless in some form to their application. The wireless could be Wi-Fi, Bluetooth, NFC, Bluetooth Classic, it can be anything. The specific webinar we're talking about here is actually some of these lower ones down here under the LPWAN, which are the low power, wide area network. So let's look at the definition for what that means. So an LPWAN network is defined as something that is low power. It can be deployed at large scale, and it has a long range. So if you look at my little graphic here trying to illustrate what are some of the 3 key features of LPWAN, it's range, geographical coverage, but also in most cases latency, because in many cases latency is a required aspect of an LPWAN network. Of course, there are cellular technologies, which is the green one, which covers most of these types of technologies. But the cellular technology, of course, comes with a monthly subscription fee, and this is one of the key differences between LPWAN and cellular technologies. And then, of course, there are other wireless technologies like Zigbee and BLE, and these are known as home area networks and not really in consideration for this talk here. So the number of connections for LPWAN, again here by a research paper down below, the number of wireless connections are set to increase between 2015 and 2020. And so this is an older paper and showing that the connections for M2M cellular will grow from 310 to 700 million. And again, the LPWAN connections actually will grow from 20 million to 800 million in the same time frame. So this is what is happening in the industry, and this growth is expected to continue in the future. The main market segment that has been driving growth for the last 20 years has been smart meters, and it will remain the top segment with about approximately 45% of total LPWAN connections expected also in the future. LPWAN applications can be used at a range of different end equipments like transport, utilities, smart cities. So of course, this is where the main focus has been over the last 10 to 20 years. But as the LPWAN technology becomes more mature, more standardized, more widely adopted, it will find its way into many other technologies. Especially, we are seeing a lot of interest in transport and logistics, agricultural, and other industrial segments. We are seeing a lot of interest in LPWAN technologies here, and we will discuss those further. If you look at the various types of wireless protocols, there's a lot of different protocols available, and then each customer needs to make a choice which one is best for their end application. And on my little chart here, I've just mentioned a couple. So we have, they're not mentioned in any kind of order here, but just talk about some. So we have LPWAN can do both private networks and public networks. And the difference here between private and public means that it is either with a monthly subscription or not a monthly subscription. Or you can also look at a different way. Do you need to build your own gateway or not? So for instance, for Sigfox, NB-IoT, and LTE, these types of technologies, there are service providers out there that are deploying gateways on a massive scale, and all you need to do is make a gadget. But then you need to pay somebody a service fee. LoRa is the technology that bridges both of these gaps. They are able to do both public and private networks, and this is why LoRa is also seeing a significant adoption over the last decade. There are new technologies coming out. We are investing heavily in a new technology called MIOTY, and which I will discuss also a little bit later in the presentation here. And of course, also there's wireless M-Bus, and then this is the one that we think is going to be a main driver for Sub-1 GHz going forward, or LPWAN technologies, and that is Wi-SUN. And that is the point of getting to a standardized Sub-1 GHz protocol, and therefore driving prices and also adoption rate higher. So we see Wi-SUN as being very critical for the future of LPWAN technologies. Of course, down here, we have the home area networks like Zigbee and Thread, and they're kind of outside the discussion for this discussion here. So what is the characteristics for a good LPWAN system? And that is typically that it has good sensitivity, which means that you can turn the good sensitivity into good long range. And we typically set a target of trying to achieve 120 dB or better at 5 kilobits per second. And then you can question, why did we set these two targets? So of course, this one sets the good link budget, and we'll look at the equations of those later. But the 5 kilobit per second sets the type of applications that can be achieved with LPWAN. We believe that going crazy and going low to like 50 bits per second, you end up with a network that might have great range, but it is not able to solve any application problems. Because remember, for most of devices nowadays, you want to be transmit some kind of ID, and you also want to have encryption, and that means that the minimum payload in many cases is 128 bits. And if you're transmitting at say, below 100 bits per second, it would take more than 1 second to transmit just the minimum basis of data, and therefore we consider these ultra-low data rates as being fairly not that useful for these types of markets that we're going after. So our target is really to try to be to achieve the best range we can at 5 kilobits per second. Then how do we go about doing this? There are two main ways of doing this. You can either go down and look at narrowband technologies, or you can look at trying to code the signal and spread the signal out across a wide frequency spectrum. Narrowband signals has the benefits of adjacent channel rejection, interference, because it is narrowband, and some standards actually require narrowband technologies. There are regulations in both Europe and North America that require narrowband, but there are also just technical advantages with narrowband. But in some cases, wideband is required, and specifically one here for North America is the 500 kilohertz FCC rule that we have to be compliant with for some use cases, and where then coding could be an advantage. So for the next couple of slides here, I'm just going to talk about the three different kinds of LPWAN technologies that we could have. Here is the incumbent, and that is GSM or some kind of a cellular technology. This has been around for almost 20 years, and therefore there's almost universal coverage throughout the entire world of these cellular technologies. But they do come at a high cost. The chip cost is high, the licensings are high, the monthly subscriptions are high, but it does work very well. It supports various different data rates from somewhere in the low kilobits per second up to into the megabits per second. But then this is where our focus is at TI, is really trying to come up with the best narrowband FSK system that can compete with the other technologies. And so here we are proposing an FSK-based narrowband system that also has flexible data rates from approximately 2.5 kilobits per second up to 250 kilobits per second, and we can operate at any of the normal ISM bands worldwide. And this enables low power end equipments like 10-year end node operation on two AAA batteries. Most FSK technologies are supported by private networks only. LoRa is a different technology supported by Semtech. It is a patented PHY, so it is not one that we do support actively today. But it does provide very good range, and I will get into a little bit about why that is later. It does have a limitation on its data rate to a maximum of 50 kilobits per second, but it does support the same low power end equipments that we also support with FSK. I said earlier that LoRa supports both public and private network, but in the public network, we are seeing some service provider fragmentation, and coverage remains an issue. So if you're looking at a solution there, GSM versus this, there are still some limitations on LoRa networks. So here we have just a second poll question. What are the 2 to 3 main requirements for a wireless system that you would want to implement in the future? So do you require the long range, or is it, are you interested in standard space solutions? And is wireless over-the-air security and authentication a key consideration, or is it really the low power that is the most important part of this question? And I'll pause here for 1 second, giving you guys a chance to hit the submit button. And here, this is also, again, it's interesting and also very common that low power is the most important factor for consideration for these types of networks. I really appreciate these fast feedback here. This is very interactive. I like this. So let's look at digital communications basics, and then I'll get into what is being done and what can be done to improve link budgets on just the digital communications backend. So at the high level, what you want to do with a digital communications link is to transmit data from A to B. This is easy when you are, for instance, say on the moon and there are no other interferers. Then this is a fairly easy task, and you can get very good range because the only limiting factors are the noise figure and the gain of your hardware. But in most applications, there's going to be interferers, and I'll have a slide about that in a second. So let's look at the receiver characteristics here. So first of all, to achieve good sensitivity, what is sensitivity and how is it measured and how is it obtained? First of all, there is a noise floor in the environment. So if you have just a 50 ohm resistor and you hook it up to an LNA, it will have a certain amount of noise energy. And this noise energy is typically just denoted as minus 174 dBc per hertz. So this is the noise energy that an antenna will have all by itself at room temperature. Then the next thing that is influencing the receiver is the bandwidth of the signal occupied bandwidth. So therefore, the more narrow your signal is, the better link budget you can get. The next one is the noise figure of your front-end LNA. So in many cases, as I write down here, the typical noise figure for an integrated LNA that is inside of an SoC is approximately 7 dB. This is better. You can get better LNAs today if you go and buy an external LNA. It is fairly easy to obtain sub 2 dB. The reason that a typical SoC is relatively high is that it is a compromise between power consumption, noise figure, and also that we typically have the ports merged between the power amplifier and the LNA, effectively hurting the LNA's performance because it is hooked up to the PA pins also. So this really comes down to a cost of the end equipment of the gadget that is being built. The last one here that is not commonly disclosed is the signal-to-noise ratio that is required by the modem to demodulate the signal at a certain bit rate. And for FSK, it is about 7 to 8 dB at 1% bit error rate. But are there other options than FSK? And that's what I will discuss in the next slide. So yes, there is. There is a theoretical limit of what the SNR can be for any kind of modulation, and that is called the Shannon Limit. This limit defines the required signal-to-noise ratio to decode 1 bit at some certain occupied bandwidth, so say 1 bit per hertz. This defines a lower limit for what can be achieved with any kind of modulation. There's nothing that can get better than that. And BPSK and GMSK are quite close to that limit. They're within 0.2 dB to that limit. So this effectively means that this green line that I'm showing here is the Shannon limit. And then what we have here is that I'm showing ASK and also FSK, and you can see here that they're somewhere between 4 to 5 dB worse at a given bit error rate. And that's what this little graph up here is called. This graph up here is affectionately known as the waterfall curve of a digital modem. So what can we do to make FSK receivers, or why did we choose FSK receivers over BPSK receivers for all of these LPWAN technologies historically? And the main reason for that is actually complexity of the device itself. So these transceivers have been in the market for some time, and typically it requires a DSP to be able to get into the BPSK signals because you need to extract the phase information out of the signal. As the technology evolves, this is becoming possible to do on less and less silicon overhead, but all of the existing devices in the market today are based on FSK. But I do see in the future a migration from FSK to some kind of a phase-based signal. So this is my prediction. So my prediction is we will get about 3 to 4 better dB of SNR in the future. So if you look at amplitude shift keying, this is actually the oldest modulation that is used, and this is essentially just on-off. Is there a signal or is there no signal? There is large problems with OOK and amplitude shift keying, and I would not recommend using this technique for any new installation. However, we still support this on all of our chips for backwards compatibility with devices that have already been deployed over the last 20 to 30 years. FSK, all you're doing here is you're changing the frequency based on the signal. So whenever you have a high signal, then you have a fast frequency, and when you have a low signal, you have a slow frequency. This graph here is exaggerated as much as we could just to show it. But the spectrums look like this, and this is the technique that is used most commonly on our transceivers today. But then I was discussing phase coherent signals here also. Here, the frequency does not change, but the phase changes. You can see down here on the graphs that all I'm doing is I'm flipping the signal around, that it flips between a 1 and a 0. This is the newer techniques that will be adopted in the future, and we're seeing more and more standards like the IEEE adopt these kinds of phase coherent signals in the future, giving us back the 3 to 4 dB of sensitivity over FSK. I think I'm not going to have time to go through this slide here in detail, but this slide here again is a slide that I got from a research paper, and I'll leave this in the deck. It effectively compares all the different standards out there today and looks at range versus power, but I will leave this in the deck for you to look at afterwards. In summary, I took some of those data rates and I put them here, and I said, what if I want to achieve a low-power, long-range network that can reach approximately 30 kilometers? What kind of link budgets would I need? And so down here, I have a calculation of what the link budget needs to be. So 30 kilometers will result in a free space loss of 122 dB and also some fading loss just to make sure that it works, which means that the required link budget is approximately 138 dB to get to 30 kilometers. So then up here, I have 6 different systems. This is GSM, Sigfox, and LoRa, and here are our long-range modes. And these long-range modes, I have them for with PA, internal PA, and no PA. So then you can see down here that if you compare against a full GSM system with a very expensive antenna, that's what I'm saying up here. Of course, these LPWAN systems that we have today in the market will struggle to compare. But this is where we're going to go in the future, is to try to get as close to these, what we'll call these public networks in performance as we can, while still keeping the cost low. But this is effectively how it compares today. There is a very important thing that was just alluded to also in communication, and that is blocking performance and also interference, and that's what this little graph is trying to show, is that you will always have interferers of some sort. And here is a little graph where I just measured what is the interference level at my house. This was measured at my house a couple of years ago. I put a spectrum analyzer on peak hold for 1 minute, and I got peaks here of minus 20 dB, which is actually very, very high. So this is a very high signal strength that I'm getting at some suburban house somewhere in the middle of Dallas at 915 megahertz. So this means that these interferers are prevalent throughout all of our homes, suburbs, everywhere that you will see. So this needs to be accounted for in the products that you work with. And this is why we are a strong believer of narrowband over spread spectrum technologies, including LoRa. So for these narrowband technologies, they can withstand having a large blocker like the ones I just showed and we can still have a narrowband signal. This little box is signifying my narrowband filter. The drawback with these types of technologies, of course, is that they require very accurate crystals. But this is where our friends at NDK and companies like that come in, and they can produce very highly accurate crystals. So we actually believe that to get a really robust system for the future, we believe a combination of narrowband and frequency hopping is the way to go. And that is what I'm trying to show on this little graph over here, is that if you have a system that is a narrowband system, but it's hopping around, it'll be robust in the presence of interferers. Interferers either as a chirp signal, which is a LoRa signal. We can also interfere as a wideband but short signal, or a wideband but longer signal, or even a narrowband but long signal. And a frequency hopping narrowband signal like this, we believe, is the strongest. And this is actually one of the reasons that we are investing in the MIOTY Alliance, which is based on a fast frequency hopping narrowband technology like what I described here. There are a couple of key considerations also for other RF networks, and I will just go through them quite quickly here. So multipath is very important, and this is the thing about that. If you have a network that has a fixed installation, you can actually be in a null just to the way that the signals are either constructively or destructively interfering. Here I'm showing a quick measurement again at my house, and you can see 20 to 30 dB of fading just due to multipath in a standard house. So multipath needs to be considered. I'll skip this one here. This is the FCC slides. So here is a special case for 500 kilohertz occupied bandwidth. And so this is really the case for what do we do if we have to be compliant with 500 kilohertz for the North American market, which I'm assuming many of you guys listening to this conference call today are interested in. So as I said, frequency hopping is the best way, but what if you don't want to do frequency hopping? Then the only way left to get 120 dB at 5 kilobits per second is to use some kind of advanced coding. And that is what we're showing in here, is that I effectively need to reduce the signal-to-noise ratio by having advanced coding. These advanced coding I did not talk much about in this call here, but it effectively means that we need to send more bits per bit or more symbols per bit in order to get to recover the bit errors that are going to be in the system. So after we've done all this modem work, and you saw all the efforts that have gone into trying to achieve 3 to 4 dB of SNR, we see, and also in my career as an applications manager here at Texas Instruments, having the hardware, you can actually lose 3 to 4 dB very, very quickly. So I'll just quickly go through some of the key ones that we see. So we, of course, we make a reference layout for every single SoC that we make, and we are really wanting our customers to follow these SoCs very, very carefully, especially because we use differential pins on our devices here. So these signals here coming out here actually need to be phase matched. This means that we need to have symmetry and equal length of our devices, or else the performance will fall off fairly quickly. What we also see is we see a lot of people doing some kind of a ground idea where they said, well, this decoupling and this decoupling capacitor, we can just merge this on the top surface and then connect it to a via to ground. But a via to ground is an inductor, and then you are effectively creating a path between two supplies. This could be a digital supply, this could be an analog supply, and then you have the digital noise propagating into the analog supplies. So whenever you're doing decoupling, this is hugely important to make sure that all of these individual decoupling capacitors, they have individual vias to the actual ground plane. And we also have this notion of return currents. And the return currents is a little bit of, it sounds sometimes like black magic, but it really isn't. You have to consider that for every transistor that sits on board the SoC, either the RF or whatever, the digital, it is sending out energy out into this pin. This pin is a single-ended pin, which means that it needs the ground to return the energy or the current that it has sent out. That means that it goes back onto the ground plane and is trying to find a way back. But in this picture here, this is a two-layer PCB, and you can see there's actually no return current here. And that means that the current is going to be forced to take wild detours around this PCB. And these kind of detours, they will hurt the performance of the overall system. Here again is a couple of examples of what not to do. And here's actually a multi-layer board where somebody thought we did this as a demonstration, but somebody thought they did a great job, but then they cut out the background plane in order to enable some kind of route on the back. And these little bitty cutouts that people put in, they hurt the performance of these RFICs tremendously and should be avoided at all cost. Again, also looking at sometimes the layout here, you can ask, why did we put the components the way we did? And here's actually 3 ways of laying out the same 3 components. And this one is actually better than this one. And this is because there's going to be cross-coupling between these 2 components down here, and up here there's not going to be cross-coupling. And up here, the reason this one is not as good is that you have a little bit of additional inductive path here. So these are some of the little tricks of the trade for doing a good RF layout. We do have, so this is a really good layout here. This is a perfect ground plane, and this has been done well. So we have application notes on our website that talk about this in more detail, and we also have some simulation guideline app notes also on our website that talk about this in more detail. So with that, I think I'll go to the final question of the day, which is, what are some of the main use cases that you're interested in using wireless for? Are you interested in smart grid, agricultural, asset tracking, building automation, smart cities, or consumer electronics? And with that, I will go to the, that one did not get to update fast enough. Oh, this is a little bit uncommon for me that it is exclusively consumer electronics. This is interesting, and thank you for that feedback. Oh, here it is. That's the rest. This seems more, okay, there it is. That seems more reasonable to me. So with that, so there's a problem with my slide deck here. Can I get help from the presenters to take me to the Q&A section?
All right, well, we have some time to sneak in a couple of quick questions, and since a few of you have already submitted some, we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located on the bottom of your screen. Okay, so the first question we have here asks, what is your opinion about the effect of the emergence of 5G technology on low-power wide area networks? Are these networks still going to survive after 5G? How is NB-IoT revised in 5G-enabled systems?
Yes, I think that's a great question, and something we think a lot about is what is the competitive landscape going to be between 5G and LPWAN technologies going forward. I find that with any kind of 5G technology, there is going to be some kind of subscription. I do understand that the subscription costs are going down in the future, but they will never become zero. And this is why I believe that LPWAN will always have a home. There's also a second consideration to make, and that is for a lot of our customers, especially the grid customers, they require the infrastructure to be operational for 20 to 30 years because they have to guarantee to their customers that these devices will operate for that long. And in some cases, you cannot guarantee that a service operator will be around for that long. That service operator can end up going out of business or get bought or have moved on to other industries. So I think there is going to be a separation between LPWAN and 5G technologies going forward based on these kinds of thoughts. That's a good question. Thank you. Next question.
Okay, and so the next question we have here is, can you expand on what the 5 kilohertz FCC rule is?
Yes, so the 500 kilohertz FCC rule is its definition inside the 15.247, and it talks about 2 different ways of passing the unlicensed rules of North America. And you can either do frequency hopping, which requires that you select 50 channels or more, and you hop across the 26 megahertz of occupied bandwidth, and you need to hop every 400 milliseconds. So that is one option. But the other option is that your signal occupies more than 500 kilohertz of bandwidth, effectively looking like a Wi-Fi signal, because the original FCC spec is written quite well to basically be Wi-Fi compliant and BLE compliant. So we can choose which one to be compliant with. And for many applications, we are proposing frequency hopping narrowbands. But for some other applications, especially from a software perspective, we do understand that it is easier to be compliant with a wideband 500 kilohertz one, because then frequency hopping is not required, and this reduces the software complexity. Next question.
All right, I think we have time for one more question, and it is, how important is coaxial cable loss for these types of networks, such as LoRA? Is it as important as in other networks that use higher power on the order of watts?
Yes, so it is. So coaxial cables and the loss of anything until the antenna is very important. Typically, for most of these LPWAN installations, they are quite small, so the cable loss itself typically is not that big. So most customers that I have interfaced with, they will compensate for the cable loss that they expect by increasing the output power of their PAs. So instead of transmitting at 1 watt, they will be transmitting at 1.5 watts. But then that does not help on the receive side because there's nothing there they can do to increase that power. So the cable loss is important, but typically not hugely important. Yeah, that's it. Thank you.
All right, well, unfortunately, I'm afraid we've run out of time. If you asked a question that was not answered, we will be in contact with you soon to get you those answers. And so that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Texas Instruments for sponsoring today's event, and of course, all of you for joining. Have a great rest of the day.